Welcome to All Space Considered, everybody. I'm Dr. David Reitzel, and with me tonight, well, thank you, everybody, for joining us here live. Once again, we are coming to you live from the Leonard Nimoy Event Horizon Theater at Griffith Observatory. This is our second show back since we took basically a 3-year break from the pandemic. And with me on stage tonight is Katie Flynn and Patrick So. And also, we will have Bill Gruneberg join us and Jared Head as well, so that's what our empty chair is all about. Unfortunately, Chris Butler could not be here tonight. Hi, Chris. I know you're rooting us on from home, but he's a little under the weather, so he felt it was best not to spread it to anybody else. If it is spreadable, who knows? But he's just not feeling well, so we hope you're doing well, Chris. As always, All Space Considered is brought to you by Griffith Observatory, and Griffith Observatory is owned and operated by the City of Los Angeles and the Department of Recreation and Parks. And as always, we like to thank Griffith Observatory Foundation, who's our nonprofit partner, and makes so much of what we do possible. Our show here tonight, a lot of our technology and the stream that we're sending out to YouTube. Hi, YouTube, everybody out there. A lot of that was made possible by the generous contributions of foundation members and donors, so we thank our foundation. Tonight, we do have a great show. It is Earth Month, and we are going to celebrate that on this third Thursday of every month, except some months. Next month, we will be on the fourth Thursday, I believe. There's a reason we can't be up here that I don't even know what it is, other than I've been told be ready to do the show a week late. So set your calendars for the fourth Thursday next month. But tonight we have an Earth Month special that's going to include Earth as an evolving planet, what we need to do to maintain a habitable Earth, keeping eyes on the Earth. We're going to do a little checkup on it. And then we're going to run a couple of videos. We have one that's from our school program about Virginia T. Norwood, who just recently passed away at the age of 96. She's known as the mother of Landsat, and you're going to see a little video we've made about her that's actually for an upcoming module of our online school program. And then I pre-interviewed Tim Barrett from Millennium Space Systems, talking about satellites. We have a connection to learn from the engineers at Millennium about what they do. And then we'll do some pretty pictures and solar system weather. We'll have our sky report. We'll do an out to launch. And yes, something exciting happened today, and we will bring you some footage from that, just as it is a little fun. And then I'm going to close the show with a little bit more about climate, and then also talk about science literacy. So the climate stuff and the check on Earth will be sort of spread out throughout the show, and you'll be able to see that. So starting out, as you can see here, our beautiful big blue marble Earth, a beautiful photo from NASA. And we had quite a crazy winter of weather here in LA and California. And Katie's going to tell us about some of that craziness that had happened. So what was going on?
Yeah, well, so first, let's start with a little bit of weather. Weather is what we see every day. It's things like wind, temperature, pressure, precipitation, and it's the atmospheric conditions. So we see a lot of extreme weather events in California, and one of the most recent ones was the atmospheric river. This photo is from January 4th of this year, and an atmospheric river occurs when water evaporates and into the air and is carried by the wind. This graph here is the total precipitable water vapor, which is the amount of water in a column of the atmosphere if all the water were condensed into liquid. And this narrow band is an example of something you might have heard, which is the Pineapple Express. And that's atmospheric moisture that builds up in the tropical Pacific. So here on the left, we have April of last year, and on the right is April of this year. So this atmospheric river gave us a lot of green and a lot of snow in the Sierras. And comparable to that, the drought report, this is from last year, April 26, 2022. You can see the dark red is the extreme drought, severe drought is the oranger color, and then the lighter ones are moderate drought and abnormally dry. So all of the colors on there are still very dry conditions. And then because of that atmospheric river and what we've had going on this winter, this is the drought report for April 18th of 2023. So a lot better conditions.
Yeah, that's actually looking really pretty darn good. So is this a sign that was that climate that was doing this? Did we have a dry climate for a while, now we have a wet climate, or was this just a wet year for weather?
No, weather is not climate. So weather is what happens every day. So this is not climate change. This is not climate.
Okay, so weather's sort of what you get, and climate is what you expect to get, is one way to think of it. And
right.
weather is day to day, what you're getting, whereas climate is sort of long-term weather patterns. So if we continue to see patterns of drought for many years, and then 1 year of a lot of rain or 2 years of a lot of rain, and this happens over 30 years, and that never used to happen, that would be a change of climate that would happen. But it certainly is interesting because it was an unusual year, but one unusual year isn't necessarily a sign. You can't point to one storm and say that was caused by climate change. It's an overall change that has to be happening in what's happening on the Earth. So our little happy Earth there, but our Earth, this is our home. This is our planet where we live. This is, what keeps us habitable, and we're out in space. That photograph there is real. You don't see stars because the Earth is so bright. The stars aren't activating the detector at all. But why are we still here if we're in space? I thought if I just went out in space, I would die due to the vacuum. Well, Earth comes with a habitat. You think about a spacecraft, you have to have sort of a habitat module, the thing that's going to give you your oxygen, that's going to reprocess the CO2, that's going to keep it the right temperature, that's going to make sure you don't freeze. You go into the night side of the Earth, you have to turn on the heaters. You go into the day side, well, you need to worry about thermal overload because the sun is so incredibly hot. So you need to do a lot of things on a spacecraft just to stay alive. Earth does that for us. But has it always been that way? And the answer is, according to Chris Butler, who would be here tonight, the answer is no. And he talks about years ago today, he was going to do another segment on that. I'm going to do my best, Chris. I'm sorry. We're just going to really show his beautiful artwork that he's done. And he's inserted Griffith Observatory into the location. So he is saying 4,600 million years ago, where Griffith Observatory is, it was basically a lava lake. So Earth had just formed. The moon, you can see there in the background, has formed. We've had the giant impact that made that. And then we fast forward a little bit. Well, now we have some rocky surface where, and this is hypothetical, we're not really sure there was an outcropping like that, but this is typical of sort of the first land that had solidified. You have lots of lava around, volcanoes. Then you start to get precipitation. The oceans start to show up. So you get lots and lots of rain. And there is a little Griffith Observatory in there. It's hard to see, but I know he put one in every picture. So there's a little, where's Waldo, or where's Griffith Observatory for you? So this one's a little easier. So 3.8 million years ago, things have calmed down. You still have the atmosphere is changing, though. Atmospheric conditions are going on. I forget when the mass die-off was, the oxygenation event. It was around, anyway. I'm not going to quote. I should have taken notes on this, but poor Chris only let us know very recently he wouldn't be here. So about 2.5 billion years ago, this is about what it looked like, but Griffith is underwater. And in fact, most of the Earth is underwater at that time. And for most of of Griffith Observatory's history, well, the land that Griffith Observatory is on, for most of the history of that land, it's been underwater. Of course, Griffith Observatory itself hasn't been underwater at all. But for most of the time, the land that's here, it's been underwater. Some of the time, it's frozen. There were snowball Earths where the Earth was completely frozen over. Some of that has to do with cycles in the orbit of the Earth. The resonances that happen, you end up getting, the tilt changes a little bit, and essentially you can freeze over the Earth. It's not so great for the life. You get mass extinctions when that happens. So, but there's our wonderful observatory hanging out there. Then, of course, things melt. You start to get plants. Look, plants are showing up. And these are slides, and these are artwork that Chris has done for our online school program. We are going to be teaching the kids about the fact that Earth hasn't always been the same. It's been changing throughout its entire history. And right now, that change that's happening is, look, we've got plants. So pretty cool. And we have, you can see along the coasts, he's added in that green. So we have algae and plants, the first plants coming into land. A little puddle there with some desert-looking plants going on. And finally, lush jungles. And we all know what happened 65 million years ago. That's right. It was the impact that took out the dinosaurs. So that was a massive change for the folks that are on Earth. So the life on Earth and Earth itself evolved together. So if a massive impact happens or massive volcanic eruptions, that can change the environment. So Earth is not always habitable, or the habitability of it can change. Plants, animals, life forms can get used to it a certain way. You have a massive impact. It can change the Earth enough that you change the life forms that are there. So of course we all know that we're not hunting the woolly mammoths anymore. So those aren't there. We got rid of them. And then of course today we have our climate, but it's different. So things are changing. So some folks might want to know, well, is that just the nature of things? Is Earth always going to change? And the answer is, well, yeah, Earth is always going to change, but it's not always the organisms as the agent of that change. So in the past, there were some organisms that showed up that dumped a bunch of oxygen into the atmosphere. That killed off all the life that couldn't handle the oxygen. So that the life forms changed the atmosphere and then had a mass extinction because of that. So there are those that fear we're doing something similar now. We're adding a lot of carbon dioxide to our atmosphere, and the question is, what's going to happen with that? It's a little bit worrisome about all of that. So, stepping forward here, here's our beautiful blue marble Earth. But Bill is going to tell us about something up here. Bill, come and join us. Bill Grunenberg, you can grab your microphone. Yay, Bill. One thing that we think has made Earth habitable is actually plate tectonics, believe it or not. We believe you need to have that recycling of the crust and of the ocean floor in order to sort of lock in the carbon. The sea life and the shells that they're making. A lot of that detritus gets down to the ocean floor, gets compacted, forms rocks. So those rocks get recycled into the earth, and it gets locked up. So that carbon gets locked up. So it's a way to recycle the atmosphere and process it. And we think maybe Venus ended up like it did because, well, we don't see evidence of active plate tectonics on Venus, although there is evidence of an active volcano, and maybe we'll talk about that next month. But Bill's going to tell us plate tectonics. Have they always been here? Did it kick off early? Is it kick off late? Is it only a million years ago that we started getting this? So what's the story?
I think it was actually much earlier than that. If we go to the next slide here, this is how we know about plate tectonics and what's going on inside the Earth. Is we have earthquakes, and earthquakes are the waves created by the earthquakes are measured on seismometers, seismographs, and people study this, and they can learn a lot about the internal structure of the Earth just based on how these waves change or sometimes disappear completely as they travel through the Earth. And this is our seismograph that you can see right down in depths of space. And of course, on the left, you can jump up and down and make your own earthquake, which is lots of fun. Yeah. Next slide. So this is an image, or this is a little animation. Yeah, it starts here, of how these tectonic plates actually moved around and morphed and bumped into each other and ground against each other, and eventually became roughly the world that we know today from all of our maps. And of course, this is not done. We're just at this point in that change, but it's going to continue changing over the next billion years or so. And here's all the stuff that can happen when you have moving plates. I'm not going to go into all of it, but if plates are separating, they're divergent. That means that you can get matter or stuff from underneath. For instance, the seafloor can come up and create things like hydrothermal vents. If plates crush together, they can raise mountains and volcanoes. But one of the interesting things they do is something called subduction. Two plates are really pushing against each other, and one goes underneath the other and shoves up mountains and volcanoes. But that has some consequences. So I'd like to go now to the next slide. The question is, all this plate tectonics, when did it start? How early in Earth's history did plate tectonics begin? And of course, we had a molten Earth, so you didn't have plates, and it had to cool enough so these plates formed at the surface and then started doing their bumping and grinding and stuff. And also the other question that this study asked, and we tread very lightly here. This is a very very healthy scientific skepticism here. But did plate tectonics start before or during the point when life started on Earth? In other words, that begs sort of that. It sounds like there's a causal connection. We're not 100% sure about whether we are on board.
The researchers were careful to say they were not implying a causal connection between the two.
But they did ask the question: did it happen around that time? Anyway, so
yeah. My hypothesis on that is this is how you get people to read it. You throw in start of life, all of a sudden it becomes something interesting to see, and it is interesting. So what did they find?
Scientists shocked. That kind of thing. Okay, so this is sort of the Earth, starting to form, and perhaps plates would have happened by now. You can see rocks and things. Now this is a zircon. You can see from the scale there that the zircon is a tiny, tiny, tiny little bit of mineral. And they form in magma, they form in lava and molten rock, and they can also form in a second heating of rock if rocks are starting to cool and they heat up again and become almost hot enough to go molten again. That's another point when these can happen. And they're really interesting little time capsules because they form and they tend to trap inside a little bit of matter from their environment. So when we find them, and by the way, they're also kind of impervious to chemical change, to all, anything that can kind of erode and change other minerals really has almost no effect on these. So they're pretty much pristine over billions of years. And all you have to do is date them, which they can do, and figure out when they were formed, and then crack them open with a laser. That's what these little black holes are here, that they're laser points where they pull out the material inside and analyze it. And what they found is that the chemistry of plate tectonics, and there is a chemistry caused by the plate tectonics. There was a really interesting study I happened upon from 2019 where the Indian subcontinents went north and smashed into the Eurasian continent and pushed up the Himalayan mountains and all of that. They found that created a wholly different oxygen level in the ocean, which is really interesting. But this shows that the kinds of chemistry that we expect around plate tectonics, if you gather zircons near where that's happening, and the kinds of zircons that you can find from as much as 4.2 billion years ago are really similar. And so what they are saying in this particular study is that that means to them that since the chemistry looks like the same chemistry that is caused by plate tectonics now happened back then, plate tectonics must have been happening then also. So it could be as much as, they say, 4.2 or more billion years ago is the bottom line.
Yeah, so now does that correlation mean that it caused it one way or another?
Well, I think we all know that correlation, as we'll see on the next slide, does not equal cause. It screwed up my title. Correlation does not equal causation, and I love this little illustration. It just made me giggle.
Yeah, then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, statistically.
That just made me giggle.
So now, what's this study about? I know
There's more stuff about plate tectonics. These are some people from University of Alabama, or they led the study, who went down to Antarctica and set up, I think it's 15 stations of seismometers, or seismographs probably, to record what was going on all over the southern hemisphere. And they went down there like 4 times over 3 years, so they really got a lot of data. And this is, of course, what this has nothing to do with their study. It just has to do with the fact that we know what the internal structure of the Earth is because of seismology. But what they found is that there was subduction that happened a long time ago. They date this back a long, long time ago. I don't remember the exact number, but it's in the billions of years. Took a whole ocean seafloor and subducted it down, and it continues to get moved by the I'm totally blanking.
Convection.
Go back. No. The what's this? The mantle. Sorry, the mantle. Yes.
Yeah, the mantle's in convection, though.
Yes, right.
That's the currents.
Right. And convection from heat below is actually what drives plate tectonics too, because it makes this mushy stuff move around, and then the plates move. But what they found is that this area of, it's called ultra low velocity zones, and it just means that the seismic waves that they measure there move very slowly. They're much slower than lower velocity than other waves. Anyway, and that is what taught them that at basically the entire southern side of the core, right at where the mantle meets the core, there is this section where this whole seafloor, this rocky stuff, exists. And it really is it's a very thin layer. It's like 3 to maybe 25 miles thick all around the southern part of the core at the point where the mantle reaches that. So they kind of extrapolated that and said, well, if it's the whole southern part, it probably is the whole core. So there is this ocean stuff that is just, ocean floor that is way down where rocky stuff shouldn't exist. The rocky stuff is generally going to be the crust that we walk around on and the top of the mantle. Once it gets down there really shouldn't be rocky stuff, and there's a bunch of rocky stuff.
Yeah, well, whether it's rocky stuff like the stuff up here, anyway, it's denser, so it's weird. It's definitely strange that it's denser material.
Yeah.
But again, that comes from the animals and the life forms and the seashells getting compacted, forming a dense ocean floor, and then it gets subducted down. So who knows? Anyway,
the Earth
interesting
does amazing
stuff.
things.
So plate tectonics has been around for a long time, and it's also altering the mantle chemistry. So how important this is for life, how important this is for maintaining a habitable Earth, we don't know. It could be important, but someday it'll stop, and we might need to worry about that. It might happen before the sun dies. We don't know. We'll have to see.
Yeah. Well, there's the headline that comes up with their conclusion that the ancient Earth floor likely covers all of that. Okay.
That's right. We've reached this part of the month. Great. Well, thank you, Bill. Sure. Sorry about that. I'm losing track of the show already. So now we use earthquakes to monitor what's going on down inside the Earth, but we can use satellites, of course, to monitor the Earth itself. And we're working on this next little video we're going to show you for our next module of our school program, our online school program, that is. This is all about a woman named Virginia T. Norwood, known as the mother of Landsat. The video opens up with footage from the first rocket that made it into space with a camera that took footage. So you're going to hear an old-timey report about that, and you're going to see that first footage, and then where that inspirational view of looking at Earth from space, where that led us. So I hope you enjoy this. You're the first people to see it. We're still working on it. This is a draft version of this, but it's coming along quite nicely, and I want to thank Ella for putting this together for us, who couldn't be here tonight. She's also a little under the weather. Something's going around.
At White Sands, New Mexico, the huge missile takes off. And the flying camera automatically takes over. The huge projectile drops the Earth behind at the tremendous speed of 4,000 feet per second. The rotation of the rocket causes the planet to spin before the lens, and the camera photographs the Earth 65 miles straight down. The horizon, 720 miles away, and the curvature of the Earth are astonishingly apparent in this still picture from the film.
Observations of Earth have been made since the very first space flights. Throughout the 1960s, images taken from weather satellites and missions prior to our first steps on the moon provided a new perspective on our planet. A few bright minds thought, could satellites be the best way to keep our eyes on our planet's changing resources? A program named Landsat was created to do just that, and its success is in part due to a physicist known as the mother of Landsat, Virginia T. Norwood. Norwood worked as an expert on receiving signals and transmitting data, and was chosen to design a scanner to make observations of Earth from space. No one had made something like this before. Still, she set out to design something that could meet the research needs of many scientists in different fields. She understood that different colors contain different information. Green easily shows off vegetation, whereas blue shows off lakes and streams. To make the most of the observations, she decided to observe in different colors, or bands. She and her team assembled the scanner with parts from different suppliers and faced much skepticism on whether it would work. To calm their customers at NASA and USGS, Norwood sent a small team on a road trip with a model of the device to take pretty pictures. Of course, it worked as designed. Once the device launched on Landsat 1, it outperformed the existing technology at the time and became the standard for space-based land observation. 50 years later, with technology that evolved from Norwood's original concepts, Landsat satellites are still showing us about our changing planet. Virginia T. Norwood's excellent design decisions early on defied all cynics and led to one of the most successful Earth observation programs ever. The Landsat program is one of many used to understand Earth's climate. NASA and the European Space Agency have fleets of satellites that make detailed observations. Some observe the oceans, measuring temperatures and wave heights. Others measure the flow of carbon dioxide around the globe. This network of satellites provides climate scientists with the information they need to accurately predict how the Earth's climate will respond to changes we make. It is important that we base our plans for how we respond on the data gathered and the predictions that are made. Science is more than just information. It is an extension of our own survival skills. We make observations and draw initial ideas of what is happening. Then, we design experiments to confirm our ideas or prove them false. The ideas that are confirmed through repeated observations and experiments we accept as fact. Observation is the key to understanding Earth's climate. If we want our planet to be habitable for us far into the future, it is best to make our decisions based on what we learn from the observations we make.
So, as you can see, we do teach a little bit in these, but also we just kind of like to let the story happen and let the kids kind of absorb it. And satellites are super, super important. And I recently had a chance to head down to Millennium Space. Well, anyway, I got to interview Tim Barrett at Millennium Space Systems, and he is an engineer that works on satellites. And, well, I'm just going to run the video. I think it's self-explanatory, and you'll hear a little bit about it. So,
well, I'm here at Millennium Space Systems with Tim Barrett. Tim, I understand that you have a connection with Griffith Observatory back in the past, but tell us a little bit about yourself, what you do here at Millennium, and also what did you do at Griffith Observatory in the past?
I'm an associate tech fellow at Millennium. I run the avionics and RF group and have been here 10 years. So I get the joy of building spacecraft. Before that, I performed the laserium shows at the observatory for 9 years. It was the longest running live attraction in Los Angeles up there. It's premiered in 1973, and so its 50th anniversary is coming right up. The most amazing building you could be in, with a great show like that and the most amazing views of the city of Los Angeles. Just incredible.
It's been a pleasure joining you here today at Millennium Space Systems. Great to have a connection like this here with Boeing. And they did fund our school programs, believe it or not. We have a grant from them. So we thank you for that.
Thank you so much for visiting us today. I really appreciate it.
Yeah, now I'm an astronomer, of course, and I grew up a fan of astronomy, but even I went to Laserium one night with some friends, and we had a good time. It was a lot of fun.
Over 2 million people came up there into the planetarium based on Laserium.
Well, that's really, really fantastic. Now, that somehow has brought you here to a career in STEM, essentially. What is it that you do here at Millennium Space Systems, and what happens here?
At Millennium Space Systems, we design and build high-performance small satellites. We fly them in groups called constellations to perform national security space missions, like missile warning and missile tracking. We take them from build to orbit in as little as 12 months, which is an incredibly short timeline, and it gets the job done.
Wow, now that's a surprisingly short period of time. Now, do folks already have in mind what they want these satellites to do when they come to you?
Sometimes they do. We're in the process of building them sort of on an assembly line now, and we're able to pull them off and modify them for exactly what the customer needs, and that's how we get there really quickly for national security needs.
Now, can you see these satellites up in space? I know that I've seen certain things go over, but what are we looking at when we see things up there?
That's true, you can. For about an hour after sunset and about an hour before dawn, when the sun is on the satellite and the sky hasn't lit up yet, you can see things. For example, you can, with a little bit of planning, you can pick out the International Space Station, which is pretty amazing. We have another case where Ellen Glad, a young researcher here, is taking telescopes in the back parking lot and looking at our wide field of view satellite, looking at it, and then seeing if she can detect it, which she did, and then I was able to verify that with our 5.4 meter dish in the back parking lot and the RF signature and see it. So that was an incredible experience for both of our teams to show that we could do that.
Wow, that's a lot of fun to do. So now when you say a dish, you're picking up like radio waves from it in addition to seeing it with the telescope?
Absolutely. Those two things together allowed us to verify that what she saw is what she thought she saw.
Okay. Now, at All Space Considered this month, we're celebrating Earth Month. And and of course with Earth Day and a real focus on the changes that are happening here on Earth, can satellites be of any use to help us understand what's going on?
They certainly can. NASA put up satellites in something called the A-Train. 4 satellites with 15 sensors on them at all different wavelengths. They're all in the same orbit, and that provides an amazing ability to compare their data and find out things like they're watching for rainfall, cloud cover, carbon emissions, even volcanic activity. Bill Pritchard at Cornell is actually predicting volcanoes now by looking at minute changes in the Earth, and that's coming from satellites, which is sort of mind-blowing.
So now this tracking of greenhouse gases with satellites, this goes beyond your typical weather satellite that used to just be able to watch the storms come in. We're now able to track changes in climate with this technology.
Certainly. Different things of ground-penetrating radar in a variety of different ways to look at things like vegetation and where it's changing. They can be watching for the ice caps and ice sheets moving very easily, visually, obviously, but lots of other things too in terms of depth and penetration. So the radars are getting incredibly powerful.
So now I know that NASA supports a lot of these missions. How does Millennium Space Systems come into play with that? Do you work with NASA?
We do. We have a mission called Tracers with the University of Iowa. Craig Klitzing is the principal investigator for that. I went to school there, so I'm excited to see this thing go. Tracer's job is to look at the Earth's magnetic field. And the goal there is to figure out if it's changing, which is always sort of true, but how much, and then why is it changing, and what's it doing out there?
Yeah, well, space weather, the sun is connected with that as well. Our very own Katie Flynn at All Space Considered talks about that each month. So how does that impact satellites? Do you have to take any precautions for your satellites to avoid these coronal mass ejections and these flares that happen?
We do. They're built generally to tolerate much of that, right? So we do have to take care of that, and we're very interested in the amount of energy that's going by during those types of things. So they're generally built to handle that. In extreme cases, yes, we could pull things together and hide or turn away from the sun if that were important, and sometimes it is.
So kids that are interested in STEM today might not know exactly how what you do connects them to STEM. What should they be thinking about to get excited about science and technology?
Well, almost everyone has a phone in their hand. That phone is incredibly powerful and needed to be designed by somebody. So you've got a whole electrical engineering, mathematical sort of background there. But then also, almost everyone is tied to GPS satellites right now. I can't go across the country, I can't go across the city, I can't find McDonald's without GPS these days, right? Or my friend's house. Not to mention, where am I? So these days, my kids have grown up expecting to be able to find themselves with that. Well, that's because of those satellites. That might give you a reason to want to do that, find a different way to do that, or keep them running, or build new ones. It's around us, and there's no going back.
Now, if a young person wants to get involved in STEM and wants a career in science, what's the best way to get involved with that? Do you have any suggestions for them?
Sure. My son got fascinated with a video game called Kerbal Space Program, which is amazing. It's actually a pretty decent representation of how we fly satellites and move them around. He did that. As it turns out, we've even hired some people whose initial spark of orbitology came from Kerbal Space Program. So anything like that piques your interest and gets you going, gets you moving.
I am also guilty of playing Kerbal Space Program as well, and I have to say I had a little Kerbal astronaut stranded up in space. He couldn't get back down.
Certainly, if you like that and it does pique your interest, it's an awesome reason to stay good at math and science, robotics, physics, those sorts of things. I wasn't very good at math when I grew up, but I find it fascinating to be able to derive formulas you had to learn in school, and that turned out to be quite engaging and quite fun to do later on. So I'd say don't give up.
Don't give up. And interest in telescopes, and interest in lasers like laserium, being involved with technology in general, I think gives the kids a sort of a head start on a lot of this stuff, I think. So thank you so much for this opportunity today at Millennium Space Systems to be able to talk satellites and Earth. Now you're bringing them technology and science and the future at your current job. So thank you so much.
Thank you very much for having us. Really appreciate it.
So, thank you, everybody. It was a pleasure to be down there. In fact, we've got a lot of folks from Millennium Space Systems in the audience tonight, including Tim. So thank you so much. It was great. So thank you for joining us here tonight. And it was great to be able to ask some questions about satellites and see what they do and see some of the technology that's down there. And I hope we get another chance to do more, or maybe bring one of their engineers here live, and we can then ask the really hard questions, like what's all the secret stuff you can't talk about? Okay. They won't tell us. They won't. It's all behind closed doors. But I do. It's important work, though, both keeping us safe from missile launches and things, but also missions like tracers, looking at the magnetic field and how that changes and what's going on with space weather. And speaking of space weather, it's time for Katie to show us some beautiful pictures of the Earth and talk about that space weather, what's been going on.
Yeah, so starting off with some pretty pictures. This is an ISS image of the Earth. This is the Himalaya mountain range. Very beautiful. And then this actually, if you didn't see, happened today or last night for Australia. Yes, Australia, Exmouth, Western Australia. This was a total solar eclipse. This was captured by Alexander Krivanichev, who sent this to me this morning, so thank you so much for that. It's a beautiful image. This is Mount Shasta up in Northern California, taken from the ISS. And then the beautiful poppy bloom, this is from our very own David Pinsky from the Antelope Valley Poppy Reserve. And then we have a beautiful, I believe this is a sunrise over an inversion layer. This is from Oliver Schwen, who takes incredible photos. And then this one was sent in by Ella, who you heard about earlier. And this is kind of a what do you see in the sky, in the clouds type of picture. Does anyone have anything fun?
They're everywhere.
Otter is such a good
close.
guess. I love that. We should have put an otter on there. This is what Ella had in mind for what she saw that day. It's tardigrade. So that's wonderful. And then this is really cool. This is an elf, and this was captured by Walter Benata, I believe. And ELVIN is emissions of light and very low frequency perturbations due to electromagnetic pulse sources. So he captured this incredible image, and I'll show you a video in real speed in just a second. This is about 100 kilometers high and 360 kilometers wide. And let's just take a look at this at normal. Okay, there we go. Wasn't playing. I just have to wait for it.
Wait for it. Wait for it. I think it's playing.
It doesn't seem to, what?
You broke
what happened? I definitely want to show it, but I don't know how now. Well, we'll just get past that, but it happens so quickly you can hardly even notice that it's happening in the sky. So for him to have captured this was just incredible, and Space Weather even commented that it's probably the most incredible picture of one of these from ground level, from Earth. And then this looks like a comet, but this is actually Mercury with its tail. This was taken by Dr. Sebastian Voltmar on just a couple days ago, April 12th. And then on to some solar system weather. This is from April 3rd. This is our sun taken by David Pinsky. And sunspot count is very strong still, highest in the past 10 years. You can see the gray line is the uncertainty. The actual data is the black, and then the official forecast is the red. So July 2025 is when we were expecting solar maximum to occur, but we're kind of on that trend already. This is from the 7th of 2023, and just take a look at this sunspot right here, 3256, because this caused an X-class solar flare right in the bottom right there, and caused some radio blackouts across Earth. And what's interesting about the X-class solar flares this year is that there have already been 7, and compared to 2022, that's how many we had the whole year for X-class solar flares. So very, very strong things coming out of the sun right now. This is that study that came out that is predicting that the solar maximum is actually going to happen sooner than 2025. So a paper was published in January that is predicting that it might come a year earlier. And that's because of this thing called the termination event, which is a period of time when the magnetic fields from one solar cycle abruptly die, allowing the next solar cycle to take over. And the sun's magnetic field is about to flip. So if you can, the bottom graph shows the solar magnetic field
should
data.
we be worried about that? The magnetic field flipping? You hear prophecies of doom if the Earth's field flips.
Well, for the sun, that's what happens when we get the end of our solar cycle, which is generally every 11 years. So that's when we also get our solar maximum, which is a lot of sunspots. And then on to some beautiful aurora images. This one is taken by Dr. Sebastian Voltmer as well. You can see Cassiopeia there, and of course, that beautiful waterfall. And this one is a little enhanced. That's Polaris right in the middle. This is taken by Jeroen Strachan, who did brighten Polaris and added some streaks to it.
Just a little bit.
But it's an incredible image. He's an incredible photographer. And what's cool about this image is that purple color are actually aurora borealis. And he said you couldn't see those with the naked eye, just with the camera. Oh, before I play this one, this is from the University of Alaska. And I absolutely love this video because it's capturing aurora, but it also captures something else that you'll see here.
Wow. Flyby of a spiral galaxy.
Yeah, so that that would be very cool. This is from the 15th. That was actually a Falcon SpaceX rocket launch that occurred, and when the fuel gets released, is that correct?
Yeah,
that's when that
gets expanded out. Yeah.
Thank you. That's when that happens. So then a beautiful image there. And that's it for Pretty Pictures in Solar System Weather.
Well, thank you so much for that, James. And now it is time for our sky report.
All right.
Patrick.
Yeah, so keeping our eyes to the sky, one of the most dominant objects in the evening sky in the west is the brilliant planet Venus. And how many of you have noticed or seen Venus right after sunset? I'm sure it's unmistakably obvious because it stays there and it's brilliant and it doesn't move. It's not an aircraft. It's not a UFO or anything like that. Anyway, so
we get calls though.
We do get calls
we get
indeed.
calls.
Yes, yes, because well, anyway, let me go on. Okay, so we're just going to do a recap of what Venus was doing just about 9 days ago. So let's see if I can. There we go. All right, so 9 days ago, Venus passed by very closely to the Pleiades star cluster. It's a beautiful cluster of stars that you can see through a pair of binoculars, and it's right next to the constellation of Taurus the Bull. And I happened to take a few pictures of that encounter, and before we do that, we can see that each day as it moved past the Pleiades, how close it got. On the 11th, I took this picture from the observatory, and you clearly see Venus, and then to the right of it, the Pleiades star cluster. And that V-shaped arrangement of stars just to the center of the picture is the head of Taurus the Bull. So I was amazed I can even get, photograph stars from the observatory with all our light pollution going on. Now, the next picture is taken from the high desert, where you can see even more stars. And incidentally, I just used my cell phone to do this, and I exposed for about 2 to 3 seconds, and you can clearly see the Pleiades and Venus to the right there, and then some of the other constellations. And one of them you probably will recognize because it has 3 stars in a row, and that is Orion. I'll just highlight Venus and Pleiades. And there is Orion is visible with its bright stars, Betelgeuse and Rigel. And of course, Taurus the Bull with its brightest star, which is kind of orange in color, Aldebaran. Now, these constellations are the winter constellations, and they've already shifted towards the west in our spring season, and we're going to be losing our view of these constellations as they encounter the brilliant glare of the sun. And so this will be a great opportunity to take a look at these constellations before we lose sight of them. Now, another constellation just above those winter constellations is Gemini the Twins, and in Gemini the Twins currently is the red planet Mars. It's not very bright. It was very bright when it was in opposition back in December. It's moved farther away from the Earth, so it's much fainter. This month, as you can see with the dates there, Mars is moving through the central part of Gemini the Twins. And on April 14th, it was very close to the star Epsilon Geminorum. Unfortunately, it was cloudy, so I couldn't get a picture of that, but it would have been really great to have seen that. Taking a look at our evening sky, so what can we see for our sky gazers and for anyone that's learning constellations in the sky? Of course, the winter constellations are nice and bright, and they're easy to see. You know, Sirius is the brightest star in the sky, and it resides in the west at the moment. But the spring constellations dominate our skies right now, and they're Leo, Cancer, and Hydra. Now, we're going to go to the next picture here, because this, I'm going to show you a series of pictures which were taken by Anthony Perkett, our telescope demonstrator, who goes out once a month during new moon and takes pictures of the sky and deep sky objects. And he took this wonderful image of that region that we just saw there. You can clearly see Leo the lion. The head of the lion looks like a backwards question mark, and the hindquarters is just made of a triangle of stars. The brightest star in Leo is Regulus. And then below that is Hydra the water snake and Cancer the crab, but they're so faint, you really need to be in an area that's far from city lights to actually see them and discern their shape. Now, as a bonus here for Cancer the crab, which is a very faint constellation, and there is a beautiful cluster of stars located in Cancer the crab. It's called the Beehive Cluster, or Messier 44, and it can be easily seen with a pair of binoculars, and even shown in this photograph here. This cluster of stars through a telescope and with time exposure is really beautiful. You can see there's blue stars and older orange stars here. Most of these stars are about 3.7 magnitude, so they are hard to see from the city, but easy to see from suburban areas or rural areas.
So the blue stars, those are hot young stars, right?
That's right. That's exactly.
That's a throwback to All Space Considered like 12 years ago.
Yeah, for anyone who's
who's still watching. Hi, Mom.
And just give an idea of how far this cluster is. It's 577 light years away from Earth. But in the sky, if you can, you will see it if in a dark area. It occupies actually about the size of the full moon. It's really big. So. All right, so we're going to move on to another bunch of constellations, and these three are the Virgo, Crater the Cup, and Corvus the Crow, which you've not heard of, but there are also faint constellations below Virgo. Virgo is the largest constellation in the astronomical zodiacal constellations, and during September 16th to October, October 30th, the sun, it takes 44 days for the sun to move right across this constellation. Of course, we can't see it because that's when the sun is in that region of the sky. But this constellation holds a lot, I shouldn't say holds, but there's an area of this in this constellation that has lots of galaxies, known as the Virgo cluster. And two of them we're going to highlight because Anthony actually took pictures of them, and the M87 and Messier 61. And we'll go and start with M87, which this is one of the largest. It's actually a supergiant elliptical galaxy. It's just about 55 million light years away, and this galaxy is really massive. It has about 6.6 trillion solar masses in this galaxy. So it's just incredible. But what's incredible about this galaxy is that it has a jet that emanates from the galaxy. And with Hubble pictures have shown this, that it stretches for a few thousand light years from the center of the galaxy. And that jet comes from a supermassive black hole, which in 2019 we got the first image that we've ever seen of a black hole. And this is not invisible light, this is in radio light. This is the heat from the gas, which is all that bright orange material that's orbiting the black hole. It's the first time we've actually seen this, and I know, David, we've covered this story.
But there's an update.
There is an update which came out just a few weeks ago. Using the power of machine learning, that image was actually enhanced and sharpened so you can see even more details. So machine learning made sense of all the data from that fuzzy image in 2019 and created what is a very sharp, high-resolution image of this incredible supermassive black hole in that galaxy. I think it's just amazing.
Where can our audience see a picture of that galaxy themselves?
Why? Actually, they can go right out the doors and look at this incredible thing that we call the big picture. It's an exhibit. And that area of the sky that's covered in that exhibit is a tiny portion of the constellation of Virgo.
Yeah, it's in our Gunther Depths of Space.
Yes.
And be sure to come see it here at Griffith Observatory if you haven't. It's spectacular.
Yes, it is. All right, so from a supermassive galaxy to one that's very similar in size to our own, M61. So Anthony took this. This is known as a 7-pinwheel galaxy, and it's just about 100,000 light years across, which is the same size as our own galaxy, containing roughly about 100 billion stars. So beautiful image. All right, so in a couple of days from now, on the night of the 21st to the morning of the 22nd, is the Lyrid meteor shower. Lyrid meteor shower, sorry. That's in November. And we'll see roughly about 18 to about 20 meters per hour during its peak in the early morning of the 22nd. So it's, if you're up during that in the morning, you can see a few bright fireballs, which usually this shower produces.
Yeah, and it'll actually be a pretty good one to see because the moon doesn't get
the moon. Yeah, the moon is very near to a new moon, so the conditions are very ideal for this, for observing this shower. All right, just a few interesting things. On this 22nd, the moon is just below Venus, and you can take a look at that. You can see how far Venus has moved from the Pleiades, which we showed with the pictures earlier. From the 11th. And then on the next day, the moon is just above it. It's a beautiful crescent moon. This is a wonderful time if you have to take a picture of it, even with your smartphone, because they're really sensitive to even faint light. And so you can get your own celestial pictures of Venus, Taurus, and even the Pleiades.
And send them into Katie for our pretty picture section.
Yes, please.
Now, so in the evening we have two bright planets, Mars and Venus, but the other planets are not visible. Jupiter's too close to the Sun at the moment. Mercury is too close to the Sun. But the other planet is in the morning sky. So if you're up early in the morning, you can get a glimpse of the planet Saturn, which is not far above the eastern horizon. So that's all we have for this month. So we'll talk a little bit about next month, in next All Space.
Well, excellent. Well, thank you for that, Patrick. Much appreciated. Well, I think the time has come for Jared to join us. I believe. Good luck. Have fun. We'll see you later, Jared.
Yes. Oh,
We're all out of here.
I'll take that from you.
Yeah, give him a clicker.
So, yeah, thank you. So,
Oh, by the way, let me introduce Jared properly.
Sure.
Jared is one of our excellent museum guides here, but also is, well, let's just say he also works in the aerospace industry in addition to working here. Knows a lot about rockets, and Chris Butler, who started our Out to Launch segment, decided he wanted to have a little growth and work into other regions, and I thought, well, Jared is our man to do this. So thank you for joining us on stage tonight.
Thank you for having me,
Yeah,
and thank
absolutely.
you, Chris, for letting me take up the saddle, if you will, for this. And of course, we want to talk first about Good Luck, Have Fun from Relativity Space. This was their first launch of their Terran 1 launch vehicle, and everything's looking nice and good. There it goes. This was from the Cape in Florida back in March, actually just after our previous Allspace. This is a exceptional launch and a very exciting one because Relativity Space is the company that 3D prints their rockets. So this rocket, Terran 1, is 85% 3D printed. So this was essentially a proof of concept that showed that, yes, you can actually build a rocket that is 3D printed and can survive the forces of launch. The first stage worked great on it. It's powered by methane and liquid oxygen, so that's why they had the beautiful blue flame happening right there. But there was a little bit of an issue on second engine start, so we could see the second stage start there. And then it kind of gutters out a little bit, and is it coming back? Okay, we're good, and no, maybe, okay, guess not. All right, okay, why don't you come back real quick? Okay, we'll try that again. Okay, let's try it. Okay, so as you can see, they had a problem starting the engine on their second stage. It's looking like ended up having a problem with their fuel turbo pump. And it basically dumped a little too much in there at startup of the combustion in the engine, and that choked the engine. And then you actually saw the engine attempting to restart itself. So the engine didn't give up, but the fuel getting into the combustion chamber did, unfortunately. But they have decided that their Terran 1 rocket was so good that they're going to go ahead and skip building Terran 1s, and they're going to go to their Falcon 9 competitor, Terran R. So hopefully within about 3 to 4 years, we will see a rocket from them, which will be a Falcon 9 with both a reusable first and a reusable second stage as well. So,
wow.
Good. So a little bit more than just good luck, have fun to them for doing that. And then also we have a very cool mission that I wanted to talk about called TEMPO, which is Tropospheric Emission Mapping of Pollution. And what's so cool about this, why are we talking about rockets in a show about the Earth? Well, this was launched on a Falcon 9 as a part of Intelsat 40E. So this is actually an instrument that NASA has attached to a commercial satellite in geosynchronous orbit. NASA and Intelsat came together to attach that instrument, and it's now measuring pollution up in orbit. And it is doing so on a almost minute-by-minute basis. Originally, with some of the things that they're looking at, like ozone and particulates, they would get data every 3 to 4 days, and then it would be like a 300-mile swath of that, and then the resolution would maybe be 10 miles or so out of that. But now with TEMPO, they're literally doing the entire Earth every hour down to, they said, neighborhood levels of resolution with that. So a very big upgrade for all of those scientists that study that for them there. And then, of course, we got to talk about JUICE, the Jupiter Icy Moons Explorer. So excited about this mission from the European Space Agency, and it took off on a Ariane 5, as we like to say, a little rumble in the jungle going out of there from the Kourou Space Center near the equator in South America. I love the Ariane 5 because it just gets out of there so fast with those 2 solid motors that it has on its first stage with it right there. And also, because it's near the equator, we often lose it in the clouds almost immediately. And then, about 30 minutes after launch, they confirmed separation, and JUICE is now on its way to Jupiter. It'll arrive there in 2031 and then go into orbit around Ganymede in 2034. So,
dying to say that the juice is loose, but I don't think we're allowed to say that anymore.
Yeah, that may not be the best.
It's
the
not.
best. I don't think it's the best metaphor, at least for this. With
I'm
it
glad
here.
it got a few laps, though.
And then, of course, they always say bury your lead, right? Because we have to, talk about something that happened a little bit earlier today.
Nobody cares. Just skip it.
Yeah, actually, let's go
Let's
and
skip
skip it. But I'm going to go ahead and just let it speak for itself. It's the one we've been waiting for since SpaceX announced they were going to be building a massive rocket back in 2012 before they revealed it officially to the world in 2016. So let's just listen in and enjoy what we're looking at.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 3, 2,
Starship Super Heavy has 33 engines on its booster stage, and by the time it cleared the launch tower, 3 were already out.
43 seconds into the test flight of the inaugural Starship vehicle, tower cleared, we're into pitch over. Propulsion reports first stage engines nominal. What a sight when the ground cameras at Stardust.
Yeah, now we're down 4 engines.
Twice the thrust of a Saturn V heading to space.
And as was mentioned, it's twice the thrust of a Saturn V, so about 15 million pounds of thrust. I heard a report today, people 25 miles away felt the ground shaking.
Going through the period of maximum aerodynamic pressure.
Let's take a look at those engines. How are they running? Let's get a little close up
As the
here.
velocity increases, the density of the atmosphere is decreasing.
Pull out.
Lessening stress
Kinda
on
looks
the
like a
vehicle.
hockey-
The call
hockey
out,
player's
next
smile.
two now.
So we got some great footage from NASA space flight.
And I love that crackle. That's
Yeah.
the same crackle you get with the Falcon 9 launch.
Yeah, Methalox crackle now. Since this is powered by methane and liquid oxygen. And you're going to see something happen here which you typically don't want to see with a rocket. Just a few seconds here. That's usually not good. So.
And also it looks a little tilty.
Yeah, and you notice it's starting, the plume coming off of it's getting a little symmetrical, which is not good, and also we're starting to lose attitude control. I did end up finding out that actually the roll that it was doing was intended, but then it lost control of itself during the roll. So that's not good. So rocket's going sideways, not good.
And begin a boost back maneuver for landing in the Gulf.
It's
No.
And now it's starting to roll way beyond its control authority, its ability to actually keep itself oriented. And then essentially, they did hit the FTS, the flight termination system, to end the launch. Basically, explosive charges that blow out the tanks. And there goes the booster, and there goes Starship with it. So big cloud of liquid oxygen and methane as well with that. So I guess we'll just kind of look at that again, and then why not? Let's look at it at half speed as well, so that way we can enjoy the beautiful thing. Now, Booster 7 and Ship 24 here were not actually expected to survive the flight. So in terms of flight testing, which is what today was, carrying nobody or any cargo on board, it was essentially a task failed successfully in a sense of things with it there. But flying for about 4 minutes, they were able to get that data, and that's ultimately in a flight test, that is what matters. Data gathering, not necessarily hitting all of your objectives. So failure is the key to success. And then this was from the GOES 18 satellite. The little arrow of number 1 there is pointing out the contrail from super heavy starship that they were able to see. Number 2 there is pointing out the shadow of the contrail in the clouds. And then number 3 is a detection of lightning in the middle of a place where there's no clouds. Well, it turns out that's actually where they finally activated the flight termination system for it there. So they detected it on that. And here you go. This is what was originally supposed to happen with the flight today. We were supposed to see the booster go up. It wasn't going to land particularly easily in the ocean, but they were going to at least give it a try. And then Starship SN-24 was going to continue in almost a full orbit around the Earth and then re-enter off of the coast of Hawaii. But this is actually what ended up happening today. So thank you, Chicken Lentil on Twitter, for making a more accurate chart for what we actually ended up seeing. And then, of course, just to let you know, your upcoming launches with an orbital velocity through May of 2023 at Vandenberg Space Force Base, one that we know of now for sure. On April 25th at 6:02 in the morning, Starlink 3.5 with Falcon 9 from SpaceX. We've also got a very interesting launch coming up from Firefly Aerospace on their Firefly Alpha called TAC-RS-3. This is a program that the United States Space Force is beginning to run now that is basically them coming to a company and saying, hey, I need a satellite up in 48 hours, get the rocket going. So, we're going to see how well they do with that. So they've had one success and one failure with their flight of their rockets so far. And then sometime in May, we're going to get Worldview 1 and 2 commercial imaging satellites launched out at Falcon 9. That will be a return to launch site flight. So the stage 1 of the Falcon 9 will come back to LZ4 at Vandenberg. So you will be able to watch the stage come back from that. And then another Starlink 2-9, sometime around the end of May. So a lot of TBAs, but that's kind of how it goes. Check out those websites in order to get those times.
Well, thank you so much, Jared. Fascinating stuff, and what a show. So now I'm going to take us back to our climate discussion about Earth, and I want to talk a little bit about how do we keep Earth stable? We want a stable environment. We want to keep it livable. We need to have a place that's good for humans. Earth, my favorite planet. It's where I keep all my stuff. We want to maintain it. So what's going on? Well, you got the sunlight coming in, of course. Some of it bounces off of clouds. Some of it's reflected off the surface. Some of it is absorbed by the atmosphere. The stuff that makes it down to the ground warms up the ground. You've heard this story before. That warmth is turned into infrared radiation. That's what escapes in the form of warmth. But some of that gets absorbed by the atmosphere. Some of it runs into a cloud. Some of it runs into dust. So there's a combination of things that happen as that infrared radiation tries to leave. Some of it does make it out. But that energy budget, you want it to be balanced. That's the basic idea there. As you can see here, this is the solar spectrum that's coming down and hitting Earth. You can see extraterrestrial sunlight. You might think alien sunlight? What are you talking about? Well, extraterrestrial just means outside of Earth. So that's what you'd measure in space, that orange curve. The yellow curve is the one that we often approximate the sunlight by, something called a black body spectrum. But the extraterrestrial sunlight's the actual solar spectrum, and then the terrestrial sunlight. Why is it so much lower? Well, it's going through that atmosphere. It has to pass through the atmosphere to get to us. And you'll notice over in the infrared band, there are those gaps where it drops downwards. That's because the infrared radiation can't pass through certain wavelengths of light. And it's blocked. And in fact, it's blocked. Infrared is the wavelength of light. It can't pass through certain kinds of chemicals, is what I meant to say. Certain kinds of atmosphere. In our atmosphere, that CO2 bands are primarily what's causing that. Methane bands. Water is also an absorber of infrared. So it doesn't let it through. Well, do you believe me or not? Well, I don't know. You can't see it. Infrared our eyes can't see. So the next little demonstration is a man that puts some CO2 using like a soda stream. He fills this with CO2, and then, as you'll see here, he's filling it with some CO2. He opens it up. That bottle's full of CO2 now. They're going to turn on an infrared camera. Notice the bottle's black. The infrared doesn't come out, doesn't make it through there. And you can see the CO2 gas being poured out into the air. It's black. It's absorbing that infrared radiation. So that's what happens in our atmosphere. That infrared wants to leave the Earth, and it sees black sky, and it just gets absorbed there, so it can't escape out into space. Keeps us a little bit warmer. Now, some folks might have said, well, maybe it won't be bad. Maybe increasing the CO2 isn't a bad thing. Maybe the climate will be fine. Maybe it'll be better. Maybe we'll be able to grow crops everywhere. Maybe everybody will get a free bunny or a free kitten. Who knows? But others have said, no, it's going to be bad. This isn't good. This could cost us both a lot of money. It might cost us lives. It might cost us a livable Earth. The people that have the most extreme views are saying, well, this could be really, really bad. We could have civilization collapse. So you might want to say, well, that's histrionic. People are being too extreme by going to those cases. You might say, well, what about the people that think it's going to be good? That seems kind of extreme too. And then I say, well, let's run the experiment. Let's just keep adding the CO2 and we'll see what happens. Well, we need to remind ourselves we're in that test tube. The experiment we're running is the place we live. So if the people that say we're going to destroy civilization as the climate changes are right, well, there it goes. We're done. That's not good. If the people that say everything's going to be fine are correct, well, then we're fine. That would be good too. But let's say we do take climate action. Let's say we decide to stop what we're doing. Let's slow down. Let's take serious action like the scientists are saying we need to do to protect the Earth. Well, what's the worst that can happen if the people that are saying everything will be fine are correct? We spend a little extra money. Maybe we have some cleaner air because we'll have cleaner energy sources anyway. We won't be polluting by burning coal and things like that. We'll have cleaner transportation. So we end up spending some extra money, and it's a little like insurance. Everybody hopes you don't need your health insurance, but if you do, it's a good thing to have it. So the case is, if the people that think the civilization is going to collapse, if we stop adding the CO2 to the atmosphere, well, then we save civilization. So which side do you want to bet on? I grew up in Reno, so I often think about, betting on this. And it's like, well, since I'm in on the bet and my life depends on it, I don't want to play that game. It's sort of like war games. The only smart decision is not to play. Let's not run the experiment. But the thing is, we have been running the experiment. We've known since the 70s, really, that this was a bad idea. In the 80s, people were making predictions that climate change would happen if we were adding CO2. However, the petrochemical industry has very strong interests making a lot of money, of course, to sort of cast doubt. So they were casting doubt. In the meantime, scientists were saying, this might be bad. But we've been running this experiment, so let's check in. Let's see what the Earth has been doing. Well, first of all, let's look at the temperature. So starting in the 1800s, you can see the temperature. This is in Fahrenheit. It was about a degree cooler than what they've calculated as average of 0. And now in the 1940s, 50s, we're sort of close to that 0 change. In the 70s, we're still getting warmer. We're about a degree over that now. And now we get to the 2020s, and we're almost 2 degrees over in Fahrenheit. So, okay, the experiment's being run. Is Earth getting warmer? Looks like it to me. Let's take a look at another map. Again, this is deviation, and they've averaged by 5 years. So that averages out things like El Niños, La Niñas. It averages out the weather. So we're starting to look at actually climate over this period of time. When you look over a long period of time, you're starting to look at climate. And I'm seeing more and more yellow, more and more orange. So I'm not sure how you could deny that things are changing. Now, you might still say, well, maybe it'll get better. But do you really want to bet on that? When there are scientists, it's like over 50% say it is critical. Things will not be good. Now, some of the most extreme think it's going to collapse civilization and things will be really, really awful, road warrior sort of stuff. But others think it'll cost just a lot of money. But why take any of that risk? I don't want to risk it. Land temperature anomaly distribution. This means if it's extra cold for a year, you'll be over on the blue side. If it's extra hot at a location, you'll be over on the red side. So this is sort of overall Earth. Now, you'd expect some locations to be colder, some hotter. But you notice as time is going by, everything is shifting to the hotter. And even the graph is getting skewed. There's more points to the hot side than there are to the cold side. So this is, again, we're not seeing an equal amount of extra cold places to hot places. People love to say, well, some folks love to say, well, gosh, it sure is cold. I could sure use some of that global warming today. Well, yeah, they were over on the blue side of the graph, whereas the rest of the Earth, or a huge chunk of it, was really warm. So again, that's weather. It's cold today, but in general, things are shifting. Let's take a look. Are the models forecasting things? So this was a model run in 2004, and you can see the red is the measured temperatures. The black is sort of the average of those models. This was run in 2004. They backward forecast, and they were able to match things very well. And then since 2004, you can see it's matching really, really darn well. So the people that say the models don't do a good job, they're doing a pretty good job. The blue, by the way, is the spread of the predictions. If you put in different conditions and you start the models a little differently, you'll get slight differences. But look, we're talking about, you know, fractions of a degree difference, and in general, they're in the right ballpark, and all the models are saying it's getting warmer. None of them are saying, well, it's cooling off. So there's agreement. Now, this is an even newer model, which is interesting. There's less agreement with the newer models as the climate scientists are putting more and more information into them. They're adding intricacy, they're adding sophistication into the model, but they're not getting it quite right. They're a little overly sensitive to it. So the ones in gray are sort of the new ones that we're not sure they're right, but they're working on them. So they kind of have to compare to the back. But it's interesting that the older 2004 model actually agrees a little bit better than the new models. But plenty of the new ones still do agree. So models are still saying things aren't going well, and the temperature is still going up. Now, you might want to know what's causing that. And of course, well, it's the sun that's causing everything to get warmer. We have a lot of warmth, the sun is warming things up, and it has a cycle to it. It gets brighter, it gets fainter along with the sunspot cycle. And I think I misplaced this, by the way. This got moved somehow. I don't know how. That's fine. I'll refer to that image in a little bit here if I see the other place I meant to put it. I deleted something strange. Anyway, now all of this stuff we're looking at and the monitoring we're doing is greatly helped by those satellites we've been talking about tonight. And this is NASA's Earth fleet as of 2023. You can see there's just a ridiculous amount of orbiting observatories keeping track of what's happening to our Earth. You can see some of the future ones as well. Out into the 2030s, we're adding even more of them. Earth is a planet, and NASA studies planets. We learn about them, and they study the Earth. So keeping tabs on what's happening and measuring it is super, super important. Not only to make sure that the public is convinced that we need to take action and that there's something going on here, but also what action do we need to take? Unless we really take the conditions of the Earth and know what's happening and how it's happening, you don't know what the consequences are going to be. We might not be able to solve everything, but maybe we should look into certain areas, like how we grow our food, where there's desertification, where there's floods happening. There's all sorts of stuff that's going on the Earth due to the changing temperature. And again, it's that net balance. When you get an imbalance of things, too much energy coming in and not enough energy going out, you get changes. Now, some of those satellites actually measured this. Folks wanted to know, well, maybe clouds are reflecting the energy. So maybe it's coming in, and this warming of the Earth will create more clouds. You'll have more clouds, so you'll reflect more sunlight, and that'll cool things off. Well, Ceres was the name of the program that ran this, and I forget what that acronym stands for. They have a satellite up there, well, several. It's on a whole bunch of them, and they look downwards, and they measure how much radiation is being reflected, and then how much infrared is being given off. And this is the net difference. It should stay at zero. If the same amount is being given off as being absorbed, it would be at zero. And instead, it's going up and down and up and down, and you can see this doesn't seem good. The Earth is getting more energy from the sun than it is giving off, and we have measured it. So no longer can people say, the Earth isn't warming. Yes, it is, right there. That is the amount of energy that is being added to the Earth overall. And this is cumulative, this isn't per year, but it absolutely is, energy is being added. It's not the sun. This is, you can see the sun is relatively constant. This is the energy the sun's giving off. But there is that up and down pattern that you see there. It goes up, goes down, goes up, goes down. That's that sunspot cycle that I showed earlier, that image that I said is out of place. Well, these ups and downs in the solar energy that's given off have to do with that magnetic field flipping that Katie was talking about earlier. When the magnetic field tangles up, you get lots of sunspots. The sun actually becomes a little more active and gives off a little more energy. So at these high peaks is where you have lots of sunspots. But we don't see that in the climate. We don't see an 11-year cycle in our climate. And this is like a 0.2% change in the solar energy. It's, you know, a couple of degrees out of 1366. So those of you good at math, you know, do the math. So what could it be? Well, it's greenhouse gases. That's what the scientists have been saying all along, that we are increasing the Earth's blanket, essentially. We are holding on to more of that radiation, and it's not leaving. Can we measure that? Yes, we have. They've put satellites in orbit that measure the carbon dioxide. And Patrick wanted to say a little bit about this one.
Yeah, well, you know, as what we're seeing here is data from the orbiting carbon satellite number 2, and it shows the amount in a seasonal variation of carbon dioxide globally, and we can actually see the effects of the Earth's vegetation when it does photosynthesis, which is when plants take water and carbon dioxide out of the atmosphere to produce the sugars and in the crops, and then, you know, they grow, and then, you know, we have salads on our plates and all that stuff. And also the trees take out carbon. So right now we see in November that in the northern hemisphere we have a increase in CO2, all that orange, which is being moved around by the weather systems. And that's because the trees have lost their leaves, and so they're not taking the carbon dioxide out of the atmosphere. And this carbon dioxide increases throughout the winter months and reaches a peak, and we'll get there because we're getting more and more. And notice it's all because it's just because there's not much photosynthesis going on, so plants aren't drawing the carbon dioxide to make the sugars they need to grow. So in May, it maxes out, and then because of the lag in the photosynthesis, but as summer arrives, you can see it drastically reduces, and that's because the leaves are all photosynthesizing and taking out that carbon out of the atmosphere. It's a very interesting data set shown graphically, the power of our vegetation being able to remove huge amounts of carbon dioxide in the air.
Yeah, absolutely. Now, not only that, and that's real. Those are real data. That's not faked. It looks like an art project in my mind. It's kind of beautiful. Yet we are measuring this. We're seeing it happen. We're watching Earth try to handle this CO2. And in fact, this is a measurement in leaf area. Plants, as you know, like CO2. And this is actually an argument that some folks that don't believe that the climate would change said, well, if you increase the CO2, the plants will just grow and they'll take up more of it. Well, they are. The plants are growing. We're seeing an increased amount of green by a lot, you know, up to 50% more in some locations. But that also, if you end up going into drought, that supplies material to be burned. And that just sends the carbon right back into the atmosphere. So it's uncertain exactly where this happens. Now, vegetation is a good thing. Planting lots of trees would be one of our solutions. But nonetheless, it's uncertain how this will work with climate. Like I mentioned before, we are measuring things like groundwater with these satellites. This tracks as climate does change. You end up getting droughts that happen for a long period of time. You end up getting more massive rainfall in other areas. Hurricanes and cyclones, those sorts of things, increase in their severity. We're seeing stronger storms happening. They're turning into Category 5 hurricanes faster. And then they're sort of hovering over land masses and dumping massive amounts of water, which is causing flooding in areas that we haven't seen before. Now, the problem with that is we grow a lot of food along the sides of rivers. Those flood basins are super, super fertile. And if we're going to see massive flooding on a regular basis along there, what's that going to do to the production of things like maize, which of course is corn, but the maize production isn't just for cattle, isn't just for us. Those sorts of resources are used in other products, in other parts of our economy. It isn't just food, so we need to worry about this stuff. This is another satellite that's actually tracking chlorophyll in the ocean, so we can watch the change in basically the algae and the plants in the ocean. So we're able to see that, and of course you're watching winter come and go as the snow happens there. This one's a little bit scary. Arctic sea ice. Well, we're going to look at the annual minimum. So if climate's really changing, you'd expect to be getting warmer, you'd expect to get less ice. Some might say, well, look, it goes down, then it goes back up, it goes down, it goes back up. Well, let's look at the overall trend. It's at 95, okay, things are, okay, maybe you could argue it's kind of flat, but uh-oh, what's happening here? Now the problem here is the ocean is where a lot of this heat is going. The Earth is warming up, and for a while we were thinking the atmosphere wasn't as warming as quickly as it should. Well, they started to take the temperature of the ocean, and the ocean can hold an enormous amount of heat, and that's where this excess heat is going. And as you see, the Arctic is not able to hold on to as much ice. That ice is getting less and less. We've lost millions of square kilometers of ice at its lowest extent. What about ice that's on land? Ice that's on land is, of course, that ice, as it melts, raises the sea level. The ice that's floating on water, like in the Arctic, that doesn't change the sea level at all. You can put an ice cube in your drink. It can stick up above the rim of your glass, and as it melts, the water won't flow over. But ice that melts on a landmass, like Greenland and on Antarctica, well, that's going to raise the sea level. And you can see here, over the last couple of decades, we've been losing a lot of ice, gigatons on each of these locations. So, okay, again, if climate is not changing, you'd expect to lose some years, you'd gain some years, but we have entered something different here. Now, will it turn back around and come back? I don't know. We're dumping tons of carbon into the atmosphere. Doesn't seem good to me. Sea level, yeah, it's rising. And it's speeding up. You will hear people saying it's not speeding up, that it's slowing down, doing other things. No, well, look at that curve. Does that look like it's slowing down to you or staying the same rate? No, it's accelerating as the Earth is warming up. Now, this one here is a little bit complicated, but what you want to take a look at here, the top one is measuring temperatures in the stratosphere of the atmosphere, so very high levels. The next one is a lower stratosphere temperature. The third one down is surface temperature, and on the bottom is the ocean heat content. And in the upper right is that Arctic ice area, so we're looking at the ice. The green is what would happen if we were not changing the composition of the atmosphere. The models predict that. The other measurements, the black is what's actually happening, and the blue and the red are other models. So you notice the observations are matching when we include human drivers, namely us adding CO2, and it's not matching what would be natural. So letting the sun do what it would normally do, let the orbit do what it normally does. And people love to say, well, did you include the sun? Yes, we included the sun. Of course we did. And by we, I mean humans working on this, not Griffith Observatory personally. So this all seems pretty bad, but we look at it here and say, well, we need to do something about this. This was 2021, where the CO2 greenhouse gases are coming from. By the way, CO2 isn't the only one. It lasts a long time in the atmosphere, though. Methane is stronger, but it dies after, oh, I don't know, it's a short period of time, a decade or so, the methane will go away. So we need to worry more about the CO2. Agriculture makes about 10%, commercial and residential 13%, transportation about 28%, electric power 25%, and industry 23%. So what are we going to do? We need to eat. We like our residences. Transportation, well, that's something we could tackle, although a lot of the greenhouse gases are due to airlines, believe it or not. But you look at Boeing, who, again, one of the subsidiaries is here, they're working on green fuels. So being able to fly airplanes on fuel that is entirely carbon neutral, essentially. It'll just be in a cycle. So it'll be burned, it'll go into the atmosphere, they will grow it, so sort of plant-based fuels and things like that. So that's one way to solve it. We could do that. Electric power, of course, well, wind power is getting cheaper and cheaper. Some of this is due to subsidies, of course, that are being given. But as you give subsidies, you can make more of them. You can do economy of scale, and things do become cheaper. Also, solar is getting cheaper. Photovoltaic cells are getting super, super cheap, and you see large solar panel farms out there. But also, you're seeing ones like this being built. This is not just solar panels. Those are mirrors, and they're shining sunlight to the top of that tower where it melts salt, believe it or not, and it makes a liquid molten salt that then goes down to the buildings down below and creates steam and turns some turbines. Now, why liquid salt? You might say, that seems crazy. What's with the extra step? When the sun goes down, that salt stays hot, and you can keep generating power for like 10 hours during the night. So it's self-storing. You don't need to have separate storage. People love to say, well, solar power, where are you going to get your power at night? Right here, easily. The hot salt stays hot all night long, well, for 10 hours, and you just generate power all night long. Of course, I want to mention a couple of others. Nuclear power is a possibility. People worry about that. Ooh, nuclear, Chernobyl, that's bad. Well, the newer fission reactors where you're splitting atoms, you can do it. Actually, there's some salt-based ones where you're doing things like that. They still can make some things that aren't so great. Some of the side products of nuclear reactions aren't so great, but also climate change is not so great. We can't continue to do things that could be setting us on a very bad path. So maybe as an intermediate step, we should do that. But of course, the future for nuclear is fusion. And if we can go get some, anyway, if we can learn how to do fusion, there's lots and lots of fusible hydrogen in the form of water that we can just take it and have hydrogen reactors, essentially. And that makes no radioactivity. It's a completely safe way to do it, but it's tough to do, but we're turning the corner on that. So there are things we can do in the future. Another thing we can do is let's become more scientifically literate and learn more about science and make proper decisions, proper policy decisions. Unless folks can understand the science and understand what's going on, they will fall victim to things. They will believe things they shouldn't. Now, of course, science isn't just folks doing work in a lab. It isn't just our new JWST telescope. It's actually the body of work as well. It's a method of doing things, and it's also the source knowledge, so all of that. So tonight, I started this little bit on science literacy or scientific literacy a couple of shows ago, and I'm bringing it back up tonight because of the climate change and our talk about climate. But tonight I want to talk about choosing your sources, where you go for your information. So let's think about primary versus secondary sources. So we're going to take a little detour away from climate here and think about white dwarf stars. Well, here's a live science article. This is a web page that Talk Science seems to do a reasonably good job on it. NASA scientists weigh a white dwarf for the first time using space-time trick predicted by Einstein. Wow, that sounds really, out there. I'm just glad they didn't say Einstein proven right again, because he's been proven right over and over again, and this has been proven. Well, this is an example of a secondary source. These aren't the people that did the research. They found probably a press release somewhere. They wrote an article about it. Briley Lewis published this February 7th, 2023. Interesting story, cool. But do you really believe it? This was interpreted by Briley Lewis. We might need to know how good of a science writer is Briley. I don't know. I'm not familiar. It seems pretty good to me, a little bit of a clickbaity headline. This is how NASA covered it. Because of course it was the Hubble one. For the first time, Hubble directly measures mass of a lone white dwarf. So even though this comes from NASA, this is still somebody at NASA that puts this together. And it's a NASA telescope, but it's not the people that did the research. But still, this seems a little bit more directly to the science. Then we get to the monthly notices of the Royal Astronomical Society. This is a scientific journal. This is where astronomers like myself publish. MinRAS, as we like to call it, used to be free, although I think they're going to start charging for this. A colleague of mine, Jay Anderson, is on this paper. I know him, some papers with him. But this is the actual paper that those results came from. First semi-empirical test of the white dwarf mass-radius relationship using a single white dwarf via astrometric microlensing. All right, now you might wonder, right, so why the heck are you telling me to go read this stuff? Like, I'm not going to be able to follow. Well, I'm not telling you to read it, but it's not a bad idea to go and say, did the popular articles, the secondary sources, did they even get the concept right? Because this article is actually more about testing the mass-radius relationship of white dwarfs. That's something we're not sure of. It's something we can test. Actually, as you add mass, the white dwarf gets smaller. So it's kind of cool. And this is what it was written about, but they also did use the gravitational lensing to measure the mass of the white dwarf. See, the other articles weren't wrong, but they took a tactic and they went after something they could understand and they thought would make people want to read the articles. They didn't think people would care about the mass-radius relation of white dwarfs. Astronomers care, but the general public doesn't. So this is an example of the first source. And if you go in and read the paper, it has their methods, it has what their data are, it has what they did to the data, it has what computer programs they used, it has how they modeled the gravitational well of the white dwarf. It has everything that you could go reproduce it yourself if you wanted to go make these observations and do it. And that's the key. When you want to find out if something is reliable and real, do they give you enough information to go do the science yourself? Do you know what they did, or is it just a bunch of word salad out there that you're like, well, I don't even know what object they looked at? So you want to choose your sources carefully. Also, who is the source? Look into a little bit behind it. The monthly notices of the Royal Astronomical Society, well, they're just a journal that publishes astronomy. They don't necessarily care what the mass-radius relationship of the white dwarf is. They're there to provide a resource for astronomers to go read stuff. So think about our sources. For example, let's say we wanted to learn about climate. The IPCC, the Intergovernmental Panel on Climate Change. This is a UN body. It's made up of many different nations. And getting a whole bunch of different nations to agree on much of anything is kind of difficult to do. So the fact that they're producing bodies of work and reports that they're going in and looking at climate change, I tend to think, well, wow, they came to an agreement on all this stuff. That's kind of amazing to have an organization like this that represents such a diverse group of people to be able to come to a consensus and agree to it. That seems kind of important to me. Wow, that has weight. Versus something like this, the NIPCC Report on Scientific Consensus. You might think, well, that sounds familiar. Weren't you just talking about the IPCC and maybe as... No, they're not related at all. This is deliberately trying to confuse you. This is a book, pamphlet, that was sent to like 2,000 teachers, and it's just a bunch of climate science denial. It has misinterpretations of data. They've cherry-picked data, which means you only pick the sources that give you the answer you want, and you ignore the things that deny what you want. They were trying to get teachers to be confused, frankly, and this was done by the Heritage Foundation. The Heritage Foundation is funded by some of the richest people on Earth, people that have made a lot of money in the economy the way it has been under the petrochemical industry. So again, look at the source. If you were reading this, you might want to say, well, who published it? What is their interest? What is the message you're trying to say? All things have bias. It's something the city of Los Angeles teaches us and we get trained on about our implicit biases, such that we try not to be biased with things. But all organizations, all pamphlets have it. So it's good to learn about them and think, well, what are they telling me and why, and what might their messaging be? And what is their agenda when they're doing their science? For example, ExxonMobil, probably didn't know this, they have scientists, not just doing oil, not just figuring out ways to make better gasoline and whatnot. They had scientists studying the climate all the way back in the 70s. And this came to light that their climate scientists essentially were predicting climate change back in the 80s and 90s all along. And they were getting it remarkably correct. About 0.2 degrees of changing per decade. That's about what we're seeing. This is some of the graphs they were producing. This information came to light, and Science Magazine, again, one of the most respected journals of science, published this study and brought to light, this was just this year, brought to light the fact that this oil company had scientists that were coming to the conclusion that climate change was real, that climate change was going to be bad, and it was being caused by CO2. So when you have an organization that is basically having findings that are against their own interest, well, that's a data point worth looking at. You know, if you have somebody, you know, the chef that says, I have the best food in the world, well, yeah, you're the one cooking it, you're going to say that. Whereas the chef at the restaurant next door says, yeah, the restaurant next door to me, that has the best food in the world. You might listen to it then and say, wow, the chef that doesn't even work there, the competitor, is saying how great that is. Well, this is the scientists at Exxon were saying climate change is real. They were the ones that were probably being paid to come up with the answer that it's not real. Now here's the kicker. Of course, ExxonMobil, this entire time their scientists were saying climate change is real, was telling the public it's not real. Every public-facing publication they did for a very long time was saying it's not real, there's uncertainty, who knows? Maybe it won't be bad, maybe it won't happen. And meanwhile, their scientists were saying, yeah, it's gonna happen, and it's gonna happen at 0.2 degrees per decade, and that's the rate it's happening. So we're being lied to at times. We know this, it's not a big surprise, but go to multiple sources. That's the final thing I'm gonna say about choosing your sources. Go to a lot of them. I recommend that you read sources that are against your own bias. We all have them. So go find a source that disagrees with you, that actually makes you kind of mad as you read it. But really think about it and think about what they're saying and absorb it. And then go read the sources that agree with you. Read both of them. But then also take a look and say, well, is it even? Are there an equal number of people agreeing and disagreeing? This is something the media has gotten wrong. They've often been saying, well, climate, let's put on a climate person that says it's not going to be bad and a person that says it's going to be bad. Well, the problem is like 98% of the scientists say it's not going to be good, and over like 50 to 60% of them say it's going to be severe. Not just not good, but it's going to be really bad. So you don't put on one person that's like, no, let's just keep burning the oil, and one that says, well, we need to stop. You need to put on 95 or 98 that are saying it's going to be bad, and 2 that say it's going to be okay. So, again, look at your sources, but don't just look at them evenly. You have to look at the numbers that are being published as well. So, a solution to climate change, let's pay attention to things. Let's look at where our information's coming from. Let's look at what their messaging is and what their agenda is. And when you hear scientists are getting rich off of climate change, well, let's go look at what scientists are actually making. These are super, super smart people, and most scientists I know are not making a killing, so to speak. If they went into business or went into Wall Street, they would be far, far wealthier. Climate scientists aren't getting rich by getting grants. They're barely able to run their labs, so it's a little crazy. Anyway, a final solution for us tonight that I want to talk about for climate change is the idea of dancing. Yes, dancing. Clever ways. We're not going to solve the climate crisis with any one solution. Well, these folks have made a dance floor that by dancing on it actually generates electricity. So let's just enjoy a little view of people dancing on the dance floor that actually makes electricity as they dance. So here they are. And this is original music by our own Hannah, actually. So that dance floor, it has LEDs built into it. They flash and whatnot as you dance on it. But it does move a little bit as you dance on it, and it generates power. Now, I don't think it comes with the big battery emblem that's on behind the DJ there. I think that's extra. But it is interesting, and this is installed in a club. There's at least one club that has it. I know that there are some fitness centers that have fitness equipment that generates electricity. And even out at the festival I like to go to every year out at Burning Man, there are art pieces that require people to sit down on like an exercise bike, a stationary bike, and pedal, 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 pedal until enough energy has been generated in the batteries, then it turns on the art piece and you get to see it. So there are clever ways to solve it. And again, any one solution is not going to do it. So when you hear people say, well, you can't get enough solar power to solve it, so it's not worth trying. Well, okay, that's true, but why don't we do wind as well? And how about we look at tide power? And how about we look at future fusion power? And how about we look at dance floors that you can dance on and make some energy? So if we look at a broad variety of things, maybe we don't end up with a planet that is cracked and dry and dead. Maybe we'll have the bright green future of a pleasant place to live. So that is our show for tonight, everybody. I hope I didn't depress you too much. And so remember, this is solvable. These are things we can do. We can fix it. And we now have the resources to monitor Earth and watch it. So thank you so much. And I hope everybody joins us next month. Probably not on the 3rd Thursday. It'll probably be on the 4th Thursday in May. We have to delay it 1 week. But join us either on YouTube. Thank you to our YouTube audience out there. Or come in person to Griffith Observatory and join us here in the Leonard Nimoy Event Horizon. And as always, I want to thank Patrick and Katie, Jared and Bill for joining me tonight. I'm David Retzel, and Griffith Observatory is owned and operated by the City of Los Angeles and the Department of Recreation and Parks, and we also want to thank Griffith Observatory Foundation, our nonprofit partner, and also I want to thank Millennium Space Systems for joining us tonight. Thank you so much for coming. It was great fun. So we'll see you all next month. Wait for Matthew to say, microphone's off.